So today we are going to continue on with our Sound Design 101 series by talking about FM synthesis. Last week we talked about subtractive synthesis, where you take this harmonically rich waveform like a square wave or a saw wave, and then you use filters to cut out or subtract frequencies from that sound in order to make it closer to, say, for example, a real object like a violin or a trumpet or what have you. And as time went on, we started looking at the math behind how these things are generated, and we started applying some of those rules in ways that allowed for more tone than starting with a very harmonically dense waveform. Instead, you start with very pure, clean tones. Essentially, you're working with just raw sine waves, and you combine them together to generate more tones. So let me just load up two synthesizers. One, we're going to use Phase Plant in order to actually build our FM synthesizer from scratch. And the other one is going to be Ableton's stock FM synthesizer operator, just to show you that, you don't need to buy VST like Phase Plant in order to do this. You can still use stock synthesizers. Almost every major DAW comes with some form of FM synthesizer, even if they don't label it as an FM synthesizer. And we'll get into why that is in a little bit. First, I want to do a little bit of drawing here just to give you an idea of how this is all going to go down. So let's say I have this, this horizontal line right here. And this horizontal line is going to refer to neutral amplitude. That is 0 decibels or 0 polarity in a positive and negative scale. Up here, we'll say this is +1, 5, and this is -1, right? So a saw wave, you have a straight line coming up, you have a straight line coming down, straight line coming back up, like this. I'm trying to get the angle right, apologies. And then comes back down, and then eventually it comes back to that middle line. A pulse wave is just at the positive amplitude or at the negative amplitude. It never really changes. To get to either one of these, you could think about it as, if we go back to this starting point, as you have one sine wave that does something like this. Sine wave being just kind of a pure tone. Apologies for my awful, awful handwriting and drawing skills. Not to scale. This is not a perfect sine wave, obviously. Comes back up. And at the same time, there is a sine wave that in this span of time goes woo, woo. You have two pulses here. I know my handwriting's awful, I apologize. You have two sine wave pulses in the same distance as this one main pulse. And you can add in a third sine wave that has 3 cycles in the same space as that one cycle, and 4 and 5 and 6 and 7 and 8 and 9 and on into a theoretical limit of infinity. And over time, those waves start to add up together to create a shape that is almost identical to a saw wave or a square wave. This is something called the Fourier series, spelled just like this. You can look that up on Google. There's a lot of really good videos on YouTube. In fact, I think the only highlighted video on my channel from way back when I started streaming about a year and a half ago. And the video goes through all of that mathematical stuff as to how this works. And we're going to talk about a couple of those things when we get towards additive synthesis and kind of our fringe synthesis section in probably about 2 weeks. But essentially, this is just a form of math that takes data, that takes some sort of information and breaks it down into a sequence of cycles. Like a sound wave, if you look at a sine wave, my really horrible drawing, if we took this half and then flipped it over, we're really just drawing two parts of a circle, kind of displaced over time. And as you combine one circle with another circle, like let's say I have this one that's twice as fast, you might get something that comes up and then it has this little wiggle, and then it comes down and it has this little wiggle, and it comes up. And it's the same exact thing, the same exact process as if this sound was originally made with this waveform. So let's try to put that into practice, right? And then we'll open up our good friend Phase Plant. It'll make hopefully a lot more sense as you see the process. Let me take a analog waveform of a sine wave. I'll play a low one. You might not be able to hear that actually, so I'll play it in a range you should probably be able to hear. Now let's duplicate this. I'm gonna hold Alt and drag. Whoop, there we go. Now, if I click this green plus sign right here, this activates Phase Plant's audio rate modulation matrix. We can see 4 different parameters that we can control with this audio rate modulation. And I'll explain why I call it that in just a second. We could adjust the phase, we could adjust the shift or the frequency, we could adjust the semitone or cent value, which is kind of locked to the musical pitches. And then we can control level or volume, the amplitude of the signal. Before, probably about 5 or 10 years ago, you could not actually directly modulate a sound's frequency. But one thing you could directly modulate, at least at a certain speed, was phase. And let me show you how that works. Before we even use this, let's take a step back and let's imagine we are a company that is trying to manufacture a new type of digital synthesizer keyboard, right? So if I am someone, let's say I am Yamhaha Incorporated. I work for Yamhaha Inc. And as Yamhaha Inc., I want to make this really cool synthesizer, but I want to build it in essentially a cheap way. I'm exploring with a bunch of these different synthesizer modules, and I have this sine wave. And let's say I take another oscillator. At first, we have this low frequency oscillator, which is not oscillating at the same rate as the sound source. And I can't attach it to the frequency. Let's just say for this situation, I can't get it to work. I'm not a good enough programmer or whatever to get it to work. But I can lock this LFO to the phase. And if I set this to 100%, listen to what happens when I play a note. we hear this almost musical pattern. It feels like by changing the phase, we're changing the pitch. This is connected with the Doppler effect, which is that thing where if like an ambulance is driving past you, as the ambulance is coming closer, it sounds like the sound is getting higher in pitch, and as it moves away from you, it's getting lower in pitch. But if that ambulance stopped right in front of you, the pitch would not change. This has to do with the phase of the sound wave as it approaches you. When the wave is coming closer, it is taking less time for the wave to travel the same distance, which is, in effect, making the wave faster. When some wave cycles faster, it raises the pitch. If you play a 200 hertz sine wave and a 400 hertz sine wave, which I can do pretty easily by setting this harmonic to 0, set this to 200, set this to 400. The one that vibrates 400 times a second is twice as high in frequency and pitch as the first one. What if we make this low frequency oscillator less low frequency? I'm going to play this F, and I'm going to start increasing the speed of this low frequency oscillator. I want you to hear what happens. Keep an eye out for multiples of the number, I believe 43 or 45. Just keep an eye on that. Now look, this stopped really moving back and forth. It has these little wiggles, but here it's wiggling a bunch. Right around 43, it seems to completely stop moving. 43 hertz is an even division of frequency from the note that I'm playing. So we are modulating the phase of this oscillator at a harmonically relevant, I'll say, pitch. Human hearing goes from approximately as low as 20 cycles a second, 20 hertz, to as high as about 20,000 cycles a second, 20,000 hertz, or 20 kilohertz. And you can even tell when you can hear each individual cycle, when it starts actually resonating at a tone, right? So we can impart new frequencies onto the sound by modulating the pitch. So what happens if I do that same thing with just another oscillator? Let's attach this to the phase. Ooh, what's going on there? Now, this is a big reason why I like phase plant, because it's so visual. You can see what's happening. Now, I want you to think about it in the sense of you are injecting something. Because right now, you're making the phase go up and down or back and forth as fast as another tone. And you can see it almost looks like the waveform is kind of being stretched out and then scrunched together. stretched out, scrunched together. Right here, it almost looks like there's another sine wave happening, right? You can kind of see the bumps of the sine wave almost lining up. You see that? Like this bump connecting here, this bump connecting here. It's not exactly where or why those things are happening, but I'm trying to make a connection in your head between what you're seeing and what you're hearing. This is the core of FM, or frequency modulation synthesis. We can generate a huge swath of tones by using an audio rate signal to modulate the phase or the frequency, which these two connect with, of a signal. You can also do stuff with amplitude. We'll get into that at the end of this lecture. I'm going to talk about the other types of audio rate modulation. Every modern synthesizer that uses FM synthesis is descended from this concept. In the physical analog hardware world, you don't have this problem emerge. I can just take a signal, which is just an electrical current, and insert that into another signal to control that current. It's just a matter of capacitors essentially interacting. Under the hood here, we're not dealing with electrical signals, we're dealing with math. So we have to deal with the calculation limits of those mathematical formulas. Due to the fact that in digital audio, you're not dealing with a continuous signal, you're dealing with discrete points of information that we call samples. And you only have X number of samples to do your math on per second. That's how this whole Fourier series works. Why you all can hear my voice right now is because we have that same mathematical rule coming in to create this effect being applied in some ways from me speaking into my microphone, that microphone amplifier, condenser, picking up the vibrations in the air, converting that into an electrical signal that goes down this cable right here, goes through the cable into my audio card, gets converted into a bunch of ones and zeros that goes into my computer, gets sent out to OBS, broadcast as essentially light to the internet, picked up by your computer, converted back into an electrical signal that makes the diaphragm in your headphones or your speakers move back and forth to allow you to hear my voice. If we could not do FM synthesis, it's possible you could never hear me talk. Which is kind of crazy to think about, right? This same exact concept allows us to communicate over the internet and to create a virtually unlimited supply of sounds. Now, the reason why I had this hypothetical of the Yamaha company is because the first people to do this on a commercial level were Yamaha with their DX7 synthesizer, which we can take a look at right now. And this thing was a game changer. This lovely little piece of hardware. Now, we can use this as a way to start to translate back into all the modern synthesizers that you use. Since everything is descended from this, a lot of FM synthesizers will use the same sort of routing setup. The DX7 had, I believe, 7 different what we would call operators, and they would all work together in some sort of routing. That's what you can see right here. We'll talk about that when we move on to operator in my DAW. And each one of those operators had some sort of special thing. So what are some things you can do with FM synthesis? Well, the most common modern example, kind of the 21st century example, is to make really cool bass sounds. That's just a sine wave playing at approximately 43 hertz. It's the lowest F on the keyboard. Now I make dubstep. And if we can have this oscillator that happens at audio rate affecting this oscillator, which happens at audio rate, what happens if we do this again? Let's make another oscillator, and let's plug this one into the phase of this oscillator and see what happens. Ooh, that's kind of nice. So even though we are affecting this secondary oscillator, we can see the effect that it has on this first one. And just like we could kind of see the push and pull of this waveform, we can start to see two sine waves kind of emerging into this shape. You have the overall sine wave shape. You have these big divots which match in with this, but then you have this little, almost like mini sine wave coming in. So as you start moving forwards with sound design in FM synthesis, I would actually encourage you to get some sort of oscilloscope, something that allows you to view the waveform that you are manipulating. Signalizer is a really good free one. There are also some good paid ones by, I think, Shope is a really good one. I think Blue Cat has one that's really cheap, that's really good. And depending upon whether or not your synthesizer of choice has these types of visualization options, you might not even need that. But let's try expanding this back out a little bit. Because as I mentioned, the Yamaha DX7, it has these little boxes. And these boxes are called operators. An operator is kind of like an oscillator, but it is a little bit special. An operator is a combination of a oscillator and an envelope generator. It's not just the sound source, it's also something that allows you to control the output of that sound source. You could look at this as either a one-shot or even a looping envelope. So what I'm going to do is I'm going to essentially recreate the Yamaha DX7 inside of Faceplant. Let's hold Alt. 3, 4, 5, 6, 7, and we're done. We officially have the Yamaha DX7 inside of Faceplant. Crazy how quick that works. No, but seriously, let's start seeing why we have operators and not just oscillators. We're going to recreate that same exact 3 oscillator setup, but rather than using the output of the oscillator to manipulate the phase, we're going to use the output of this amplifier with an ADSR envelope. I'm going to click that, apply it here. So far, we're pretty much at the same spot. I'm actually going to set these now to no output because you can hear we are actually hearing multiple sine waves layered on top of each other. Now, we just hear that one main sine wave. So, oops, not there, right there now. All right, so now we're very very close to where we had it before. What if I want to allow this to change over time? Let's start sculpting the overall amplitude curve of this waveform. I'm going to give this a slight attack. Just to kind of give it less of a transient. I'm going to pull the sustain down, increase the decay a little bit. Maybe give it a little bit of a release. Now, I like that, but I feel like this third one, a little bit too aggressive. Let's just kill the sustain on this one. Ooh. We have that little whipping sound. Almost like it's getting smudged. Now we have that bow, almost like a pitch decay. And now I could even start to sculpt this one. Now we have the sound that evolves over time in a way that we couldn't have had work if we were just modulating with the phase directly. It's not a bad sound, but it's very different, and I hope you can all see or hear how different these two sounds are just by changing the amplitude of the modulator, or excuse me, the carrier. This is where it's going to get a little bit weird because sometimes I mistake some of these terms. I always flip carrier and modulator, so I find looking at the vocoder is a good way to check. So when you're dealing with this type of intermodulation of sound sources, you have two different sounds to work with. You have the modulator and you have the carrier. The carrier is the sound that is affecting what we hear. We do not hear the carrier signal. What we hear is the modulator signal. So to jump back into phase plant, we could look at these three oscillators as this is modulator operator. This is carrier operator 1. And this is carrier operator 2. And we can even change how these carriers interact with each other. For example, instead of having carrier 2 modulating carrier 1, while carrier 1 modulates the modulator, this is why I'm saying it's kind of confusing to start to separate these terms. We could actually have carrier 2 also modulate the modulator. And now, let's see what that sounds like. Let's compare that with this one. You can hear how the tone changes. It's much closer to the original tone when we keep carrier 1 as a pure sine wave versus when we have carrier 1 as a more complex waveform. This is partially why you usually see people doing FM with raw, pure tones such as sine waves. Occasionally, you will see triangle waves. You see saw waves in a very special case, which we'll get to later on. And you almost never see pulse waves used as FM sources, because the more complex the waveform, the more complex the harmonics, the more aggressive the modulation is in the FM process. So let's take a brief detour and jump over to operator, because we can do that same exact process here. We can adjust these envelopes right here. You can hear now that it's a little bit less aggressive. But it's very close to the same sound that we ended up with here. But what if I wanted to switch it to this mode, where both of the carriers are modulating the modulator? Well, you notice these little squares in this menu? I clicked over to this bottom right bar right here in operator to get to it. If we go back to the DX7, oh wait, it's the same boxes. Whoa, that's wild. What's going on there? Well, before you had synthesizers like FM8, like Citrus, like Phase Plant, it was really, really hard to get the operators to work together. So they had pre-established routing algorithms that you could select between. That's what these are all referring to, and we'll go into what these mean looking at these. So don't worry about trying to understand every single one of these, because as you see the process from each of these, you'll understand the connection. So here we have 4 colored boxes. We have a yellow box, a green box, a blue, or we'll call it teal box, and then a red or orangish box. We'll say blue and red, because I'm pretty sure that's the color scheme they were going for, but the colors are only relevant insofar as they connect with these operators that have the same colors. A is yellow, B is green, C is blue, and D is red. Right now, we see that operator A, the yellow operator, is our carrier signal. That's what we hear, because the line goes directly out to nothing, but that means it's the end of the signal chain. Everyone above that feeds in as a modulator for the operator directly beneath it. So D, the operator we're not using, I could even turn it off right there. D is modulating the phase of operator C, which is modulating the phase of operator B, which is modulating the phase of operator A. If I click, this 6th operator, now D, C, and B all feed into A. You can see that these boxes now no longer run into each other. They all run into this bottom box right here. Go back to this one. And then go back to this one. See how it changes? So each one of these represents a different configuration of that algorithm. So this one right here, we have C and D both equally feeding into B, which then feeds into A. In this one, we have, looks like C feeding into B, while D is standalone and they both feed into A. And each one of these has its own type of special sorting algorithm, including this one right here, where each independent operator is seen as its own sound source. There's no FM going on. You could look at this essentially as 4 subtractive synthesizers packed into one container. In Ableton's operator, you can choose a variety of waveforms, sine waves, saw waves, square waves, triangle waves, even noise. And not every synthesizer does this, but it's more and more common nowadays to allow you to actually go in and affect the discrete harmonics of the sound in order to generate a little bit more of a varied tone. If we contrast that with a synthesizer like Native Instruments FM8, for example, you can see that there isn't that same control over an individual operator. Like if I jump in on operator A, you can see I don't have any controls in order to write in those partials, which again comes back to that Fourier transform that allows this whole thing to work. But they have even more harmonic options for you to work with to allow you to have, I think, a little bit more control over how these different waveforms work. And I actually would encourage you to, if you have FM8, go through these different waveforms and ask yourself, how could I remake that? For example, 1 plus 2. What does that mean? What does it look like is happening? Well, it looks kind of like a sine wave, but there's something else going on. We have this little dip right here. So what's happening? Well, let's jump back to Faceplant and let's look at one of the other main components of FM synthesis, which, again, since this is all about the Fourier series, we can look at these not as individual oscillators, but as components of a broader harmonic series. Now let me turn off these 2 carriers. Let me reset this ADSR envelope to the default. And then let's start increasing this thing right here that says harmonic. Keeps going up and up and up and up. I'm not changing the note. I'm not changing the frequency. Or in each of those, you can hear individual frequencies sliding through each other. With this one, it's much more steppy. And as I move it quicker, it seems like it's blending together, but that's due to the nature of what happens when you get up into these higher notes. So, another quick little tangent. Let's look at a frequency to note chart. Now, if I look at the note F0, we're looking at a frequency of 21.83 hertz, cycles per second. 21.83 times 2, 43.66. What is F1? 43.65. Basically the same exact thing. Basically 43.66. What is 21.83 times 3? 65.49. Looks like that's almost C2. Right there. What if I do 21.83 times 4? 87.32, which is about F2, which is just double 43.65. So that makes sense. We can pretty much just ignore a lot of these even numbers, because if I do 43.65 and I times that by 2, it's the same exact thing as if I did 21.83 and multiplied that by 4. It's the same, 21.83, and I multiply that by 4. There we go. So if we ignore the even numbers and we just do the odd numbers. So now let's do 21.83 times 5. 109.15. What is it right around 109.15? Looks like that's the letter A above that next F. So we have F, F, C, F, A. The harmonic multiplier is the core of all FM synthesis, where now these operators can work at ratios of each other to create more complex tones. Now that FM8 wave was called what? 1 plus 2. Okay, so what happens if I have this at 1 and I set this to 2, and I'm just going to do it direct? Oh, what's that? Oh, that's kind of what's going on here. Hold on. Oh, it looks like we have that weird little divot right there. Oh, that's crazy. So obviously it's not perfect, but if I play, let's go to operator F and let's set this to a 1 plus 2. Compare that with a sine wave. Now let's actually just output this one. Oh, it's because of that. So these waveforms right here are all just combination of harmonics. This is 1 plus the third harmonic, 1 plus the fifth, 1 plus the eighth. This is actually based off of the output of this second one right here. It could be addition. It could be the case of essentially this. Like if we turn this off, we could look at this as 1 plus 2. And if we combine these two together, let me actually turn the drive down, we can actually start to see one plus 2. This is actually addition. So I was incorrect. I misspoke and I apologize. When we're looking at these waves, we're not actually, like these 1 plus 2, we're not actually looking at FM. We're not actually frequency modulating. What we're doing is we're just adding those two waves together and then taking the output of those two to modulate our wave, which you can totally do. Let's set this to a sine wave. Let's set this one to a 1 plus 2. Let's send this in here. That's the sound of two sine waves, each set an octave apart, affecting the output of a single sine wave. So I really encourage you to experiment. Even if you don't have FM8, look up some of these shapes here. I'll just jump through them so you can kind of see one by one. I wish I could make FM8 bigger. All of these different waveforms. A parabolic sine wave is just a similar, like it's just like a more rounded sine wave, more squarey. See, like a softer square wave, a softer triangle. Some of these are pulse width modulated. I would definitely just play around, see how you can make some of these shapes and experiment with how they kind of interact together. You can create very realistic sounds. You can create very unrealistic sounds. Right now, everything we're doing is very harmonically perfect, but what happens if I change this a little bit? That's kind of weird, right? So the further away you get from that harmonic overtone series, the more atonal the sound seems to get. We went from something that was very, very clean. Sounds almost like a horn or a trumpet. And just turning this off by like 10 partials, or 0.10, 0.01%, or 0.01 of a harmonic. You get that weird kind of phase cancel-y kind of volume tremolo effect. And at certain octaves and at certain ratios, you get things that could be seen or heard as like bells. Like really up here, like you get to very bellish tones. Especially if you give it a little bit of reverb. So let's look at some additional case scenarios. Let's say I have a sine wave, right? If I pull up this sync knob right here, and we hit 2 or an octave up, and that, it sounds like every time we go up in sync to a certain multiplier, we have that same harmonic thing happening. But there's like these in-between points where it's not perfectly lining up. We get these really bright, buzzy tones. Now, in order to help understand why this happens, let's make it. Let's make oscillator sync with frequency modulation. I'm going to turn this off. I'm going to add another analog oscillator. Now I'm going to leave it on a saw wave. If I do FM from a saw wave, oh, that's weird. Notice how we're getting that same sort of divot. There's a little bit of grit right here due to the nature of the analog oscillators right here. But oscillator sync is literally just frequency modulation, or I guess phase modulation with a saw wave. Virtual Riot's sound design is 80% saw sync. If you are a Serum user and you have, like here, I'll just go ahead and show you exactly what I am talking about. Let's open up Serum with Faceplant. This is my recreation of Serum inside Faceplant. If I have some sort of wavetable thing right here, here's a wavetable doing a thing, and then I have Osc B that's set to a saw wave, and then I do FM from B. Guess what I just did? I just did sync. FM from a saw wave is literally just sync. So most of the sound design you know is just sync. It's just sync, but that's okay. That's okay. It's a good sound for a reason. It adds new octaves to the sound that we can use for sound design purposes, right? Let's look at some of the other ones. Let's grab a sine wave and let's try adding in a triangle wave. I like the shape. You can kind of see the linearity of the triangle wave injecting in. Triangle waves are probably the most common waveform besides sine waves. Since if you look at the harmonic spectrum of these sounds, let's just grab a slice EQ just to show off the partials. There's a sine wave. It's just a single tone right there. Triangle wave, it's pretty similar. You still have that big sine wave at the bottom, but you have all of these additional tones. Compare that with a square wave. Whoa! Those tones got way frickin' louder, right? And as we mentioned, the more harmonically dense a waveform is, the more it will impart tone onto the modulator. So a square wave is, like I mentioned, one of the worst ones to really FM with. A sine wave, a triangle wave. You can kind of see up here if I scrunch this in a little bit. Keep your eye right here. Sine waves are going to be the cleanest ones. Triangle, you get a bit more harmonics, so if you want something that has a little bit more of a formant. And then a saw wave, as we saw, generates a lot more tones, but you see right there, how we get to those harmonics using this saw sync effect. But let's go to a square wave. Doesn't really seem to be doing too much to the sound. And that's because, again, we are adjusting the phase of the signal based on this waveform. In this case right here, we're telling the waveform, okay, so take the phase and bring it all the way forwards here, and then slowly pull it back, have the phase all the way to the other side, have the phase all the way forward, have the phase all the way back. It's the same exact process, but instead of having a smooth curve between the highest point on the phase and the lowest point on the phase, it is telling it to just kind of linearly, directly go to that. With a saw wave, it's having that linear motion going up, but then it jumps all the way back down and it keeps that going. That's why it gets higher in pitch, because it is a uniform linear growth, but not one that is bipolar. You don't have the same motion. You have in essence, a unipolar linear response and then a reset. With a square wave, there is no linearity. It is either all the way up in phase or all the way down in phase, which if you notice, all that's really happening are we're taking this sine wave and we're kind of just flipping the polarity. Do you see that? We're not really affecting it that much. We're just flipping the polarity back and forth. This is a big reason why I don't recommend you do FM with a square wave, but you can do things with it to kind of get around that. For example, pulse width modulation, it kind of moves the square more into a saw-ish range. So as you can see, we get this little thing that's, again, it's not necessarily the best source, but it's better than just a pure pulse wave. Now, phase plant is a slightly unique case. It's not the only one that can do this, but it is one of the few that can allow for direct frequency modulation in the digital domain. As I mentioned earlier, if you're dealing with a hardware oscillator, that's just an electrical current. That's just either a smooth or a jagged or whatever have you current of voltage from like 0 voltage to maximum voltage, or from -1 voltage to +1 voltage. You can attach that voltage to the frequency control of another thing. And since it's just electric current, it works totally fine. You can directly modulate the frequency of another signal with a raw sound source. You don't have to do any of this finagling with phase. You can now directly control the frequency of a signal in phase plant. And let's listen to the difference. This is phase. And this is frequency directly. Sounds very similar. That's why you were able to get away with it, but sounds a little bit different. There's actually a preset in here, which I'm going to open up. I recommend, if you have phase plant, go through the tutorials. Trust me, go through the tutorials. It's really, really worth it. So they have it listed as kind of usual or standard frequency modulation or phase mod. When you control the frequency directly, it's going to be more of a linear slope. You heard that one gets a little bit more kind of squelchy at the higher octaves. Then, if you control the pitch-locked frequency, which means as you go up in pitch, you actually have a broader distance to cover. You get a more exponential effect. Notice how for most of this, it's pretty gentle, right? But then there's a point right around 75% or so where boom, it just blows up. Sounds pretty cool to me, but it's very hard, I've found, to get this to work pretty effectively. I would definitely recommend playing with it, but I will admit I don't do the exponential stuff super often. And then, I mentioned this before, but you can also directly control the amplitude at audio rate. This is also called ring modulation. If you are only doing it in one direction, for example, if I had something that, let's say, took this signal and then used some sort of bias control to move it only up to the top end, I could take this, and this is direct amplitude modulation, but when it goes in both directions, you have ring modulation. And this is a very, very common way of either softening sound or, depending upon the ratio, adding different tones. Like with max ring mod, listen to what happens as I increase the carrier. Remember, carrier is the modulation source, the thing that is doing the modulation. The modulator is the modulation target, the thing that we hear. . . . So the ring modulation can be a really, really fun tool that doesn't impart as many harmonics as frequency modulation. Another really important thing that I think will be important for you to notice going forwards is kind of this weird inverse relationship between harmonics and the actual waveform. So I'm going to pick a pretty complex waveform and use an example of I'm making like a dubstep bass, right? So let's just make a nice, gentle little LFO here. Now let's do a little bit of FM with a sine wave, right? That's nice. It gets kind of squelchy, kind of gritty, but it's a little bit too low. Let's just up this to harmonic 2 and see what that sounds like. That's weird. It starts to sound a little bit more hollow. Let's try 3. Now, that's kind of weird. If I look at this, we can see this shape. It's kind of like, it's not perfect, but this is kind of Sawwave-y, right? You can kind of see it kind of linearly moves down. If I set this to 4, all of a sudden we have much less of that and much more of it only at one side or another. Now, where have I seen that before? Where we have like this linear slope and then things are jumping, and then we have like these kind of more defined up and down moments. It's almost like this is kind of like a square wave, and this is kind of like a saw wave. And if we look at, it's like, let's make this maybe a slightly less aggressive waveform. Let's try something like this. A little bit too much. Let's look at the harmonics with slice EQ. When we have this at 1, we can see 1, 2, 3, 4. Okay, let's go to 2. Oh! All the even harmonics, once we got to Harmonic Multiplier 2, started to go away. Come back. Go away. So what's going on there? Well, one thing I've discovered, I will admit that I believe I first heard about this idea from Seamless R in one of his earlier FM tutorials. When you're modulating a modulator, a modulation target with a carrier signal, if the carrier is an even multiplier of your modulation destination, the thing that you are hearing, you will get square wave partials as a result. If you are doing FM with an odd numbered multiple, 1, 3, 5, 7, etc., you will get saw wave harmonics. It's kind of weird because saw waves are the ones that contain the even waveforms, or the even partials, whereas square waves are only odd partials. But you can test this. You can test this. If you go into any FM synthesizer, make a patch, and then start changing the ratios between even and odd, you will see the harmonics shift based on saw wave partials at odd intervals and square wave harmonics during even intervals. It's partially where the Terror Squad bass comes from. It's FM from an octave that is even, or a harmonic that is even, rather than a harmonic that is odd ordered or odd numbered. Keep that in mind while you're doing sound design. Saw wave harmonics as a general concept. A saw wave will have more frequencies for you to work with. It will have more what we can call textural capacity. Not a real term. I'm making that up. Please don't go around talking about the textural capacity of stuff. That's just a way for me to help you understand or maybe help visualize this. The partials that this generates are much broader in scope, so you can do more with them. A square wave has less harmonic complexity. However, it has more loudness because it spends more time at its maximum and minimum amplitudes. Minimum being negative amplitude. You can look at sort of the shape of these, and you can even clearly see, like, how long do they spend near these peaks right here, this negative peak and this positive peak. The Sawwave has this moment right here and this moment right here. Everywhere else, it's somewhere less than maximum. This is literally only maximum. It's literally only the maximum possible amplitude in positive and the maximum possible amplitude in negative. So if you're trying to make some more intention in your sound design, even if you're exploring, ask yourself, do I want this sound to be textural, or do I want this sound to be loud? Or do I want it to have more power or more interest, so to speak? And I think a good way to wrap this up would be to try and make a more realistic instrument. Let's try and make a bass guitar in Phase Plant or Operator or any FM synthesizer. So I'm gonna grab just the Scarby M bass right here. I'm gonna let this load up, and we're gonna use this as our template for recreating a bass guitar with a synthesizer. Let's start loading up a couple of analysis plugins. I want to grab two in particular. All right, so here is a bass guitar. Let's look at a couple of things. One, where is the fundamental frequency? I'm playing a D sharp near the lower octaves. We have this D sharp right here. Then we have this note right here, which is a D sharp an octave up. Then we have an A sharp. Then we have another D sharp. Then we have the normal harmonic series using Saw Harmonics. I want to be clear there. We didn't see the low D sharp and then it jumped to the A sharp. It uses every single harmonic. So we do not want to use even ratios in our FM. Additionally, I can see that the second harmonic is in fact much louder than our fundamental. You can see on the overall waveform curve, it has this kind of upwards arc. You can see the bump from the first harmonic, or the fundamental harmonic, and then all of these other overtones. So now the last thing I want to do is just play a single note. And then freeze it. Take a look at it. So in terms of amplitude, we can see it's a pretty stable waveform. This actually gives us a lot to work with. Because you can see how the waveform has this little dip, a spike, and then it kind of evens out before repeating this basic shape. That almost maps identically to the waveform. So really, all we're trying to make is this shape. Once we get that shape, it's almost entirely just a matter of getting the amplitude curve. Because as you can see, it's just a nice little transienty, plucky sound. It doesn't go all the way to silence right away. You can see it has a very long decay. If I were trying to make it ultra realistic, I would make sure that it has no sustain and only has decay, but we don't have to worry about that. So let's start building this from the ground up. Let's get a sine wave. And let's start adding in a couple of sine waves. I'm going to do this without using operators, but you can kind of take that as you will. First things first, I'm going to start adding a little bit of phase modulation here. Spectrum. So we're already pretty good there, but I think we need to be an octave lower because the bass guitar sample that I'm using is playing the lowest note on the bass guitar, but that's actually going to be played on a MIDI keyboard an octave up, so you can preserve the lowest octave for things like key switches and whatnot. So we're going to jump this down an octave. And we're pretty much there already. You can see if I go too far, the fundamental grows, but we can actually play with that. This is something that I probably should have mentioned earlier, but the phase of your carriers and your modulators are really important because remember, we are doing phase modulation here. So where your waves start and end in a relationship to each other will change the timbre of your sound. Watch this. It's very subtle, but watch this partial right here. This third partial right here. Keep your eye on that. And I could even change this one. Or I think I'm doing phase randomness there. I was holding the wrong one. There we go. That's what I was expecting to see. And even if I am not controlling that one, if I'm controlling the main sounds phase, same sort of process. So if you're ever having trouble getting a sound to work, try messing with the phase of one of your operators. But we don't need that. We were actually pretty close starting off, just with just a little bit of that. Maybe turn this down a smidge. I'm going to add in another operator that's hopefully going to help accentuate that second harmonic a smidge more. And you can go in opposite directions. You can kind of do negative pulse modulation. Let's try playing with the phase here. Try and get it kind of like that. Oh, there we go. Just for shits and giggles, let's add another sine wave directly at that second harmonic. And then make this a pluck. Compare that with our bass guitar. quite where I want it, I think. Let's try turning down a little bit of this. There we go. Now, maybe just a little bit of a very light filter pluck to go into the subtractive synthesis that we learned about last week. There we go. I could do more to make the bass synthesizer much closer to the action of the bass guitar by playing with velocity mapping, by playing with sort of the amplitudes of those various operators, rather than doing kind of some direct frequency modulation right here. But you can see how quickly you can start to create these very interesting tones, and how versatile FM synthesis is. It can be used for sounds that are very conventional. It can be used for sounds that are very otherworldly. You could even try and manipulate FM ratios to start to say certain words. Because if you notice, as I play with some of these ratios, we get these shapes. And if you started to move those around and use amplitude envelopes to have them come in and out, I'll give you a hint. You could probably make some speech with this, especially if you started introducing a little bit of noise into the signal. This will be the last thing I show off, what happens when you FM a sound with noise. You get this very almost snare-like attack. In fact, one of my favorite ways of making 808s is to take a low-passed square wave and then use a little bit of white noise either on the amplitude or on the phase. Hear that? It's like that stabbed subwoofer sound. I find that phase tends to work a little bit better for this. There is one more thing I wanted to talk about. I don't have Serum installed on this computer, but there is something kind of weird about the way that Serum specifically does frequency modulation. If you've tried to do Serum FM in a synthesizer like FM8, in a synthesizer like Citrus, in a synthesizer like Phase Plant, there is a good chance you are dealing with this issue. Serum does not have harmonic multipliers. Serum only has octave and semitone and cent-based tuning. So if you wanted to do the harmonic multiplier of 2 for FM, in order to do that in Serum, you have to do plus 12 semitones, or 1 octave up. If I want to do a harmonic multiplier of 3 in Serum, I have to do 1 octave and 7 semitones. But here's the thing. A harmonic multiplier of 3 is not the same as 1 octave and 7 semitones. Now, if you noticed, when I was doing some of the math here, based on this lowest F, the numbers weren't exactly matching up the way they should have. I was kind of glossing over that, but our tuning system is what we call equal tempered. The distance between this A right here and this A right here is evenly split into 1/12 of a ratio distance between 55 hertz and 110 hertz. Each one of these individual notes is an equal distance of 1/12 of whatever the ratio is for an octave. That carries over between these two, between 110 and 220, so it scales more and more. That's not the same exact thing as if you were just multiplying it by 3. For example, if I take this note A2, 110 multiplied by 3 is 330. I didn't do this right, I did 11, so 110 divided by 3 is 330 hertz. Multiplying by 3 should be E4. We should be seeing 330 at E4. Let's scroll down. There's E3, there's A3, there is E4. Oop, E4 is at, it's not exactly at 330. It is in fact 0.37 hertz lower than the harmonically accurate third partial. That minor inconsistency is going to create a big difference in FM. So if you want to emulate serum style FM inside of a synth like Citrus or Phase Plant or FM8, you have to use the semi-cent and adjust that accordingly. So I would have to do so that would be an octave and a perfect fifth. That's 12 plus 7. So I would need to have this semi-cent at 19 cents or 19 semitones in order to get the same effect as 1 octave, 7 semitones. And if you want to have harmonically perfect ratios in serum, you actually have to start tweaking by a couple of cents to get it to lock in. And that's a pain in the ass. So I would say don't necessarily worry about getting it perfect, because here's the thing. If 329.63 hertz is close enough for our ears to 330 hertz to accept it, then it's good enough for FM. It really is. So I wouldn't even worry about it. I wouldn't even worry about getting it perfect. Just be aware that it is imperfect, and it will change the way you do FM based on the synthesizer you use. Thank you for watching. If you're watching this on YouTube, please be sure to like, comment, subscribe, hit the little bell thing, do all that fun stuff. Maybe check me out on Twitch where you'll see these things live. Maybe consider supporting me on Patreon. It's up to you. And there's a good chance this is going to be where we're going to cut the video.